First one is by Francesca. Francesca needs no introduction in this program, I think, but she's an assistant professor, technically lecturer, but as assistant professor at King's College London. She's doing a lot of very interesting work on a lot of things now, sequential Monte Carlo and gradient flows and MCMC and all that. And today she has a very nice talk that I'm really looking forward to about unbiased estimation of smooth functions of expectations.
Thank you. Yeah, thanks a lot for the, I don't need any introduction. That's the first time that someone ever says that about me. So you will see in this talk that it's actually a very simple Monte Carlo idea, but it turned out to be extremely hard to make it work. And so the whole talk is about what was hard and how we tried to fix it. So let me start with picture of Nicola and Sumit, who are the collaborators on this work. I did this when I was a postdoc in Paris with Nicola, and we had very early morning meetings with Sumit because he's in Australia, and I put the picture up there. You most likely you know them already. So moving on to the actual problem. So let's say that you are given a function f, and you have a sequence of IID random variables with a certain mean and a certain variance. What you want to do is to provide unbiased estimates of f of m. Now, if f is a linear function, you are in business. I mean, you compute the expectation of, well, the empirical average of the xi's, and then, you know, f is just linear, so that's fine. That's unbiased by definition. If f is nonlinear, that's a lot harder than you would think to obtain unbiased estimators of f of m. So before going into the details of what has been done and how we propose to do this, let me give you two motivating examples. Those are the two that I will be focusing on in the experiments as well, but there are other functions that you might be thinking about. So a classical situation, for example, in latent variable models, is that you can get an unbiased estimator of the marginal likelihood or of the likelihood in a sort of more general setting. But what you actually want to use is mostly the log likelihood, because that's numerically more stable. So in this case, the function f is the log, and what we care about is to unbiasedly estimate the log of the, the log likelihood, and most of the time the gradient. For example, because we want to do something like gradient descent or stochastic gradient descent. The reason why we want unbiasedness in this case is mostly for, let's say, to have theoretical guarantees, which tells us that we will converge to the optimal parameter estimate with an error that we can control. Clearly, if you have very, very low variance estimates, but they are biased, you might be okay as well. But in that case, I think the theoretical guarantees are a bit less straightforward. So this is motivation number one. Motivation number two comes from a set of problems, mostly in Bayesian inference, that are un-normalised models or doubly intractable models. So those are models in which you have a likelihood. So my data is always y and my parameter is always theta, but this likelihood is known up to a normalizing constant. So the z of theta is the normalizing constant of your likelihood, not of your posterior, and is intractable. So you cannot even evaluate the likelihood. This happens a lot when you have exponential random graphs, for example, and this will be one of the main examples. And the reason why we want to obtain unbiased estimators of 1 over z, so in this case, the function is the reciprocal, is maybe because we want to do some sort of pseudo-marginal approach, whether with MCMC or with importance sampling. So we want to replace 1 over z by an unbiased estimator and then go through with our inference task. So these are the two main motivations. Clearly, you could think of a lot of other functions that you might want to do this with, and I will give some conditions that these functions need to satisfy for the approach that I'm going to describe to work. So we are going to use Taylor expansions. So clearly you need your function to be analytic, which is true for the log and the reciprocal. Is not true for other functions of interest. For example, when you have SDEs, a lot of the time you're interested in the max function. For that function, this approach would not apply at all. So, okay, let's say that our function is smooth enough and we can Taylor expand it around some x0. This is what you get. Then we rewrite it in this way for reasons that will become clear in a second. So M is now the mean of my ID random variables. X0 is the point around which we do the Taylor expansion, and the gamma k is just a coefficient that does not depend on M. The reason why we write it like that is because if we look at the log or the reciprocal, these gammas have this expression and they are bounded. They don't depend on M and they have a subgeometric decay. So the subgeometric here being crucial because, for example, another function of interest that has been studied a lot is the exponential. The exponential does not have subgeometric decay. So what I'm going to say actually does not apply to the exponential. The theory for the exponential is, however, well developed well, not this theory, but there is work on dealing with the exponential and unbiased estimate the exponential of M. Okay, so this is a Taylor expansion. Doesn't really give us an estimator at this point, but again, there is a literature on truncating a randomly truncated infinite series that's normally called a sum estimator or Russian roulette estimator. I put some references up there, which for what I know are the first papers in which this has been used, but clearly there are a lot more after those. And the idea is actually quite simple. Because that's an infinite sum, we cannot compute it. So we're going to randomly truncate it with this random variable R, which takes values in the natural numbers. And then we're going to replace the M divided by X0 minus 1, which we don't know because we don't know M, with an unbiased estimator. The classical unbiased estimator is this one. And I'm going to call this the simple estimator. Because I mean, because the xi's are independent, they all have mean M. If you take the expectation of that, you get M divided by X0 minus 1 to the K. So that's a very intuitive estimator of that quantity. And then by playing around with this randomly truncated sum and adding this probability down here, you can actually show that this is unbiased under very mild conditions on the U's and the R. So far, so good. It seems that we have an estimator and there is nothing really new under the sun. These type of estimators have been proposed before. So what is tricky about this estimator is that we need to pick X0 and it's not entirely clear what conditions X0 needs to satisfy for this to work. Then we need to pick the distribution of R and the form of the URKs. Now, we found that the first point in particular has been overlooked in the literature. And by that, I mean, most of the papers would just tell you that this works for any X0. And technically it works, is unbiased, but it might have infinite variance, which is not something that you want for an estimator. And so the bulk of this work was actually providing guidelines to pick X0, R, and the URKs in such a way that you can use this as a turnkey approach, meaning you don't need to do anything besides providing the function and the sequence of random variables. So what do we want to achieve? Well, we have this estimator f hat. We want the variance to be finite. Doesn't seem much to ask. We want the CPU time to be finite as well, because this is a random truncation. The amount of computation that we spend depends on how big R is. Because this is random, well, we want it to be finite in expectation, at least, but also with finite variance. Because if not, we might have to wait forever occasionally. And the other thing, it would be nice if we could have this random CPU time with light tails, meaning, it's very likely that we will finish within a short time. This might seem very obvious, but I will actually give you examples of other estimators in the literature which do not satisfy these two sort of basic objectives. Because in fact, satisfying them is not very easy. You need to be quite careful with the choice of X0 and R to make this work. So why we want the second one in particular, as I already mentioned, most of the time we want to do this more than once. For example, if you think about the stochastic gradient descent application, normally we would have several data points, and then those data points, the likelihoods of those data points get summed. And if one of those takes forever to run, then we are just stuck. The other one is, well, let's say we run these in parallel to save time, but if one of them has infinite CPU cost, then we still wait forever. So if you don't satisfy the second bullet point, then even running in parallel doesn't reduce your computation time. Okay, unfortunately, to make sure that this is true, we have to go through a bunch of theoretical properties. I'm not gonna go into too much detail. I'm just gonna show you a couple of expressions, but the way in which we achieved some sort of guidelines is by looking at the theoretical properties of the various estimators that are out there. So because we care about finite variance, the easiest thing to look at is clearly the variance itself. We're going to use a sort of standard decomposition of the variance, which involves conditioning with respect to R. In this case, the first term, this one, takes into account the variability introduced by the random truncation. So even if you had perfect random variables, meaning their variance is 0, so they're not random at all, you're just plugging in M, you would still need to randomly truncate this infinite sum, and so there is some variance there. The second variance term comes from the choice of the URKs. So clearly, we would like to choose some URKs that give us unbiased estimates of this quantity, but they're also nice, meaning they give us low variance overall. And it turns out that the simple estimator that I showed you before does not achieve that. And I will explain why. By the way, if something is unclear, I'm happy to be stopped at any point. Okay, let's focus on the first term. So this term, I'm just put the expression up there, is not particularly important besides the fact that there is no URK. So this does not depend on your choice of URK at all. It only depends on R through this tail probability up there. So if I define beta 0 to be this quantity, well, I need x0 to satisfy this condition. If this condition is not satisfied, the Taylor expansion does not exist. So it's not even a problem of random truncation. It's a problem of making sure that the infinite sum converge. The second condition is that, well, to make life easy, we're going to pick R to belong to a certain family, which is a geometric distribution starting at 0, just because, you know, we have a analytic expression for these tail probabilities, so we can state clearer results. You need to pick the probability of this geometric to be smaller than 1 minus beta 0. And the reason for that, I think, is quite intuitive. If you look up here, is that this is beta 0 to the 2k, and is divided by this tail probability. And once you take the ratio, this should be smaller than 1 for the series to converge. So this is somewhat already out there in the literature if you look around enough. But this choice of x0, we didn't find it to be clearly stated a lot of the time. So this is what you need, regardless of your choice of URKs. Now, clearly, you will want to look at what happens when you increase the computational time. So if you satisfy these two conditions, the first variance term is finite. We're happy with that. And if you let this probability go to 0, which means that your computational cost increases because the expectation of R is 1 over P. So number of the value of the truncation random variable tends to infinity, then this variance goes to 0. And we're pretty happy with that, meaning if we put on more computational time, randomly truncated the series provides, well, gives you smaller and smaller variance. That's all right. Then if we look at the second term, this depends on the URKs. And it turns out that some choices of URKs are quite bad. So similarly as before, we have conditions on x0, which now require you to not only take into account the sort of convergence of the Taylor expansion itself, but also the variance, the sigma square up here, of the URK, of the xi's. So these are more restrictive conditions than the one we had before. And similarly, then R is a geometric random variable with the same type of constraint using beta squared instead of beta 0. And the rationale behind it is the same. When I take the ratio between beta square And this tail probability, I want it to be smaller than 1. And so my series is converging. Okay, so what can we say about the UR case? We looked at 2 strategies, and then I will briefly mention a third one. So this is the standard strategy in the literature, which I'm going to call the simple strategy. And you can see that if we want to estimate this, we take the first k xi's and we take this product. Seems easy enough, but also seems a bit wasteful, because the way you would implement this is you sample capital R from a geometric, and then you obtain these x1 to xr, but you only use xr to compute the last term. It's never used to compute the terms before. And because you already have access to these inputs, it might be a good idea to actually use them to improve the URK. And that's the idea that we propose. So instead of using only the first capital, only the first k, we use the whole sample to estimate this URK at every iteration, well, at every value of k. So we call this the cycling estimator, because you just cycle through your random variables. So what you have up there is the simple estimator, and then you sort of translate to the following. You start at 2 and you go to k plus 1, but this expression is still the same. And you repeat this until you hit xr. So if you want to sort of get an intuition behind this, is let's say that k is 1. In the simple estimator, then you take x1 divided by x0 minus 1. In the cycling estimator, what you do is you compute x divided by x0 minus 1 for all of your random variables and take the average. And it's intuitive to say that this second one will have smaller variance. And that's in fact the case. So in fact, for the cycling estimator, the second term of the variance decomposition does go to 0 as p goes to 0. So again, more computational time means your variance goes to 0, which is the bare minimum that you want from an estimator, in my opinion. So yeah, that's what I just said. And that's not true for the simple estimator. And you also recover up to this log factor, the sort of standard Monte Carlo rate. So the variance does decay like 1 over computational time up to the log factor over here, which mostly comes from the fact that you have 2 sources of randomness, the variance of the xi's and the variance of your random truncation. The simple estimator, on the other hand, even for very, very simple examples, for example, the reciprocal, we have one example in the paper to show that this will converge to some quantity, v, which is strictly positive. So this variance does not go to 0 in general. And this will reflect in the experiments quite clearly, because the fact that the variance goes to 0 implies convergence in probability. So more computational time will give you better and better estimates. And we will not be able to see this for the simple estimator because that's just not true. Okay, so this is what we got out from the theory, but we still don't have a recipe to pick x0. We sort of have a recipe to pick R once we have x0, but we don't really have a recipe to pick x0. So what we want is this inequality to be true, but in practice, we don't know m or sigma squared. So one way to solve this, I'm not claiming it's the only one, is the simplest one we could think of, is just use the bootstrap. So guarantee with high probability that this inequality is satisfied. By that, I mean, you have a set of xi's, which mean m and sigma square. You can construct a bootstrap confidence interval from this quantity that will tell you this is true with high probability. And in practice, it works, but I'm sure that there are more refined results, more refined strategies to ensure that this is true. So once you have that, then you can plug your estimated value of x0 into to obtain p. You get your random variable r, and all goes through. Okay. The crucial point is that to do this, you need pilot runs. So this is not going to be a cheap procedure. And so the idea that you can debias cost-free, I don't believe is true. You need to carefully tune a lot of these quantities to make sure that everything goes through. So to give you one example of when these things go wrong, I will focus on the log and the reciprocal, but I will first look at the log. So let's say we are in a sort of very simple model, which is a latent variable model. You have your marginal likelihood over here. This is your sort of prior over the latent variables, and this is the complete likelihood. So what you want to estimate is the log of this and its gradient. Getting unbiased estimates of this without the log, you can do with importance sampling or other strategies, but we use importance sampling because it's us mostly, and we work on importance sampling a lot. So that was the go-to method. Let's say you sample from some proposal, you know, the usual stuff. And then you estimate these with the average of the weights. And that's unbiased by construction. So to compute the MLE, then you get an unbiased estimate of the log likelihood with the strategies I described, and then you can get the gradient with a very similar estimator that I didn't put on the slide because it's a bit messy, but it's the same exact construction. One other option to do this is a sort of importance-weighted autoencoder estimate, which to me is just log applied to importance sampling. Now, this is clearly biased. We know that's true, but it's consistent. And there are a few strategies in the literature that propose to debias this estimator, one of which is a sort of multi-level Monte Carlo, which they call sumo estimator, which amounts to getting this for one data point and then adding and subtracting these differences, and then randomly truncated this quantity. That's a good idea by looking at it, but it has infinite variance. So you have an estimator which is unbiased, which is this one. It's fairly cheap to compute, but the variance is infinite. And I'm not even going to show results for this because it just blows up very, very easily. So this has been noticed in the past and has been improved by looking at more sophisticated truncation, which involves a multi-level Monte Carlo strategy, in which case you have unbiasedness and finite variance. But you have a CPU time, which is random and has infinite variance. And if I just show you one picture, this is quite clear. So let me unpack this a little bit. So the 4 plots are estimating the log likelihood for a toy model. Everything is Gaussian, so I know the truth. The truth is the horizontal dashed black line. So you have dimension 5 up top and dimension about 100. I think it's 96, but I'm not entirely sure, down here. And you have a small value of R, meaning this is quite cheap to compute, and a larger value of R, just to show how they compare. And you can sort of see that, so the expected value of R, which is our expected cost, is the vertical dashed line. You can sort of see that when R is small, this multi-level Monte Carlo is quite far away from the truth. That's because we're adding very few terms, and we know that the importance-weighted autoencoder approximation is a lower bound, so that's expected in a way. It cannot be that good when R is small. As R increases, it gets better. But occasionally, the computational cost blows up. So occasionally, I have to wait way longer than I was expecting to. So overall, even if the estimator is not bad, sometimes it just takes forever to compute, while the cloud around here are the simple and cycling estimators. And well, they are very much centered around where they should be. So the cost that I was expecting to get and the answer I was expecting to get. Now, to be honest, even for this toy model, this does not work extremely well in high dimension, as you can already see up here. And if you increase the dimension, it's not going to work at all. But I don't think it's a problem with the random truncation. It's more of a problem with your importance weight approach, because that's high variance. And so if you then add on top of that the random truncation, your variance is just huge. But you can, well, we made it work on a higher dimensional example. This is really to show that the fact that the CPU cost is random can be quite bad if it's heavy-tailed. Okay, so let's now look at what I would call a fairly high dimensional example. I think this was in about dimension 500. So you need a very good proposal for your importance sampling there. But is ICA, which means, well, we have still a latent variable model. My latent variables are still these Z's over there. Y is a high dimensional object, in particular an image, which I will show in the next slide. These are the latent variables, and then my parameters are these independent component vectors and the variance that I have up there. So this is similar to principal component analysis, but is not the same, because in fact, I have way less independent components than my the dimensionality of my data. So in a way, it's a procedure to extract the most relevant features out of your data. So in here, I think the dimensionality of these vectors is about 100 times bigger than the Z. So what I want to do is to do stochastic gradient descent to infer my theta, given a data set from this model. Why do we want to do stochastic gradient descent? Well, because the sort of other standard procedure to deal with this type of problems in a EM type procedure, expectation maximization, which doesn't easily allow for mini batching. So when you do stochastic gradient descent, on the other hand, you can easily do mini batching. So we don't go through the whole data set at every iteration. We only choose to use one randomly picked data point. And that's the main reason why we looked at this example, is to justify why you really need an automated procedure to do this. We cannot stop at every stochastic gradient descent step to tune X0 and P. We want to do it on the fly. And the bootstrap is a good way to do it because it doesn't increase the computational cost that much. So these are the results. These are the two sort of through independent components that I use to generate the data. You can see that SAEM, because this is a not particularly convex problem, is sort of struggling to recover, to detangle the two shapes, but gradient-based methods are a bit better, surprisingly. So this is more a proof of concept that this works. I'm not claiming that you should not use SAEM, because in fact it works quite well for these type of problems. But if it was for us to see that if you tune everything properly, you can actually make this work in fairly high dimensional settings. Now, we also looked at the reciprocal, which is the other function that I discussed. In this case, the application, as I already mentioned, is exponential random graphs. So this is the type of likelihood that you have. You have a sufficient statistic over here. This is your parameter. And the data set is a sort of standard one in this literature, which is the Florentine family business network. So it's a network of 16 nodes, and you see a connection when two families interacted through business relationships. And so in our case, theta is two-dimensional, as it is mostly the case in this sort of exponential random graph. Theta is 2 or 3-dimensional. And the sufficient statistics are the number of edges and the number of k-stars. Is not particularly important. The important part is that this quantity is a sum over these many terms. So you cannot compute it. And because this is your likelihood and you cannot compute this, you cannot do maximum likelihood estimation and you cannot do Bayesian inference unless you do something about this Z. So as I already mentioned, theta is typically small. So even importance sampling would work quite well to get an unbiased approximation of Z. So that's exactly what we do. This is your posterior then. I'll be focusing on sort of Bayesian inference setup. So this is your likelihood, this part over here. This is your proposal, and this is your prior on theta. Clearly, you cannot compute this because you don't know 1 over Z. But if we could replace this with an unbiased estimator, then we have a pseudo-marginal approach. So we have an unbiased estimator of the weights, and everything goes through in the sort of usual way. You can get very good estimates of Z of theta through sequential Monte Carlo, mostly because this type of problems are very amenable to SMC. This is thanks to Nicola. I didn't actually know how to do this. So you can get very high quality unbiased estimates of this, and then you can apply a debiasing procedure to get an unbiased estimator of 1 over Z. And this is just a sort of toy, well, it's not so toy, but it's to show why cycling really matters. So in this case, I'm looking at one theta in particular in a high probability region of my posterior. I'm comparing simple and cycling for this theta in 2 different scenarios. So the expectation of R is small, and so these 2 estimators are roughly the same, or is large and they are different, and cycling should take longer to compute because it involves is a R squared computation instead of R. But in this particular example, getting the estimates of Z is the expensive bit. So it takes about 15 seconds to get each estimate of Z. So adding a few seconds, not even a few seconds, a few bits of seconds to those 15 doesn't really change much. The 2 metrics that we're looking at are the work normalized variance and the probability of returning negative estimates. So if you think about Z, Z is a normalizing constant, so it should be positive. But because I'm using a Taylor expansion to debias 1 over Z, occasionally the estimates that we return might be negative. And in a way, we want to minimize the probability that that happens. Because, well, if you have a negative normalizing constant, that's bad. You cannot do MCMC with that unless you do something a bit more sophisticated. The work normalized variance is the variance times CPU cost. So we want to compare the 2 in terms of how much variance reduction do we get if we increase computational cost. So we want both of these quantities to be small. And you can see that when R is 1, they are not very different. They are roughly the same, and they have a fairly high probability of returning negative estimates. If I increase R, nothing really changes for the simple estimator, besides the fact that, you know, R is bigger. And so this changes. But for the cycling estimator, the probability of returning negative estimates, I think there is a 0 missing here, is considerably smaller. Now, this all works because the inputs that we're giving, so the unbiased estimators of Z, have moderate variance. And we control that by controlling the number of particles that we use in the sequential Monte Carlo sampler. So we know that if we increase the number of particles by 10, then the variance will reduce by a similar amount. If you have very, very small variance estimator, let's say you use a lot of particles, then your estimators of Z of theta are very low variance. Debiasing will not give you much because you already have very low variance. So removing the bias will not give you much better results. On the other hand, if you have very high variance estimator, debiasing will not help you because your variance is so big that even removing the bias only adds additional variance. So I really think that this makes sense when you have moderate variance, and debiasing can help without hurting. Now, you can get sort of posterior plots, and you can see this is the simple estimator, this is cycling. These are the 2 dimensions of theta. You can see that something has gone wrong here and there. Those are the negative estimates of the normalizing constant. And even visually, it looks wrong. So it's very easy to detect. If we look at the effective sample size, so we repeat this procedure 100 times of estimating the full posterior, and we look at the effective sample size, meaning the variability of the weights of your sort of importance sampling procedure. Effective sample size, higher is better. And it's easy to see that cycling outperforms simple most of the time. Sometimes it can go bad. That's when you have a high number of negative estimates, but most of the time it has better performances and it doesn't cost anything more in this particular example. So to conclude, my takeaways from this work is that the biasing estimator is much harder than you would think. Many estimators that are out there, they are unbiased, but they have infinite variance. So they are not practically useful. even if they have finite variance, very often they don't have finite CPU cost. And that's less of an issue, clearly, but it's still an issue if you want to use them many, many times, because the chances that you're going to end up waiting forever are higher. And same for not having finite variance. And we found that guaranteeing this for is actually not straightforward, and you need a lot of fine tuning to do that. So we don't claim that this is the solution. It's one step towards a solution that we found is reliable most of the time, but clearly there are improvements that you could think of. For example, in particular in the UR case, we proposed the cycling estimator, but why not doing something even better than that? I'm thinking in particular about minimum variance and bias estimators that are used statistics, which, you know, we are thinking about, but we haven't done anything yet. The other message that we really wanted to convey is that debiasing does not come for free. You actually need to put a lot of computational effort into debiasing, because you need the pilot run to estimate the X0, unless you have prior knowledge about X0. But if you do, you are in a very special case in a way. And yet what I was mentioning in the last few slides is that if your variance of the inputs, meaning the xi's or the estimator of the normalizing constant, is too large, you cannot expect a debiasing procedure to give you better results. It will not help. If anything, it would make things worse. So my suggestion would be, if you have a limited computational budget and you find yourself in this situation with high variance, the computational budget should go into reducing the variance of your inputs rather than increasing the expectation of R, because that's what really matters. And yeah, I think that's all. That's a QR code that I don't know if it works, but it's there. And that's all I wanted to say. Thank you.
We have actually a lot of time for questions. Yes. So any questions? Or I will start. Oh, there's questions.
Hey, so thanks for the presentation. I was just wondering, maybe I missed something, but what exactly is the connection between estimating the log likelihood and this problem of evaluating f of m? What is, you know, if you're trying to estimate the log likelihood, what is the setup here exactly?
So let me go. Okay, you are here.
Yeah, exactly. So you're,
What you want is log of this quantity.
yeah.
So your f is the log,
Mm.
and your m is this quantity. Getting unbiased estimator of this quantity, your m,
Yeah,
very easy through importance sampling. Oh, sorry, forgot.
I see. Yeah.
But getting unbiased estimators of the log is much harder.
Mm.
So
Okay.
all of this was to, you know, I have easy access to unbiased estimator of this quantity.
Mm.
I know that if I just plug those into the log, this is biased, is not okay for me to use a bias estimator. How do I debias it?
Yeah, I see. Okay, yeah, that makes more sense then. Yeah, great.
Any other question?
Can I? Very nice talk, thank you. Maybe I missed something, but in the beginning, when you did the Taylor expansion and then you divide by x0, if it's in higher dimension, how would that work?
So effectively, the Taylor expansion is always in dimension 1, because my m, my m is always one-dimensional. In the log likelihood example, the log likelihood is always a scalar number, like the likelihood is always a scalar number,
Oh,
but
I
the
see.
integral that you need to compute to obtain the scalar number might be high dimensional.
Oh, I see. Okay, that makes sense. Thank you.
Any more questions or comments? So I have one question actually about the number of, so let's say I want to use this for particle filtering, parameter estimation. And how would I know how many replicas of, so is there like a good guidance of how many instances of unbiased estimates you need, or how does things change with respect to that
Yes.
amount of samples you have?
So a sort of rule of thumb that we found to work reasonably well is to pick, let's say that you have a finite computational budget to obtain your Xi's, that in this case would be your output of the particle filter. You divide that in half. You use the first half of your outputs to estimate X0 and the second half to actually debias. This works reasonably well when you are in a moderate variance setup. When you are in a low variance setup, you maybe can do less, more to estimate X0 well, and then less to compute the estimator because your variance is already low. So once you have a good X0, you're good to go. If you are in a high variance setup, I would just give up, to be honest, because this is adding variance and it's not going to help. But we actually have plots that I didn't put in the slides, but because this work normalized variance is a relatively tractable quantity, or at least to provide upper bounds, you can actually see that this work normalized variance is convex, and there is a soft spot where you should be as a function of P, or the expectation of R, and of the number of pilot runs. And that doesn't depend on the function that you use. It's just an upper bound, which is relatively tight. So you can actually get a good intuition of where you should be. And we found that this dividing in half was close to the optimal point.
Is there any way to get like for the variance of the estimator, get any rate in terms of number of replicas you have or anything like this? I mean, is it possible, at least you think, or it's just impossible?
With the simple one, no. With the cycling one, we have an upper bound, not an equality.
Okay.
But the upper bound decays like 1 over R, roughly speaking.
Any more questions? Otherwise, we can thank the speaker.
You.